In this chapter we have something called the Work-Kinetic Energy Principle. Actually in the book they call it the Work-Energy Principle, but they're really talking about the kinetic energy. So I've written it like that. So to explain it, I have to go and try to derive it and show you how they're related. So kinetic energy hasn't been talked about yet. And I'll just jump to the chase and tell you what kinetic energy is, and then I'll derive it. So kinetic energy is the energy of motion. Everything moving has something called kinetic energy. And the way kinetic energy gets defined, it gets defined this way: K period E period for kinetic energy. And it equals 1/2 m times v squared. Now mass, m is mass, and this thing is in kilograms, and v, it's the velocity or the speed. Now in chapter 6 we're only talking about scalars, so this is really just the speed, but v is the reason for the velocity. Okay? And that's in meters per second. And we have to square it. And anytime we talk about any energy whatsoever, we would use units. We use these units. So anytime we're talking about any energy units, all energy units have this unit called the capital letter J, and we pronounce it joules. And it's the last name of a famous scientist. His name was James Prescott Joule, and he was the one who worked a lot with energy and discovered something called conservation of energy, which we study later in this chapter. So that's the definition of what this thing called kinetic energy is. So anytime you have something moving, take that mass and multiply it by the speed, but you have to square just the speed. So if you had for example, if you had a person and the person was running down the street, let me just erase some of this. Okay. So this person is running down the street, and let's say that this is let's say it's a 100-kilogram person. That's about 200 pounds. That's not terribly heavy, I guess. And let's say they're going with the speed of about 2 meters per second. So the mass is 100, and the speed of it is 2 meters per second. So if we want to know how much kinetic energy they're using, what we have is we just take it. 1/2 the mass of this person is 100 kilograms, and the velocity is 2 meters per second, and we square that. So when we do that, we would get 2 squared is 4. 4 times 100 is 400. 400 times 1/2 is 200. So we would have 200, and the units left would be kilograms, and these things. Meters got squared also, and seconds got squared also. But we would say that this is 200 joules. Okay. So the person who's running with this mass and this speed has a certain amount of energy, kinetic energy. It's the energy of motion, and it's 200 joules. That means that their body is using up 200 joules of energy every single second. We don't use these type of units in our life, really, in my world anyways. If I go to the store and buy a food package, I look on the food package, and it'll say how many calories are in that food package. So calories are a unit of energy. So if I eat the food, my body now has added that many calories, which helps me run my body. And if I want to lose weight, I've got to find some way to kind of burn off some of the calories, and that's what's happening here. If a person of this mass and this speed is running, they'll be burning off 200 energy, joules, but food is stored up potential energy, and when we eat it, there's a chemical reaction, and later we're able to have something called mechanical energy. Mechanical energy is the energy of different types of energy, but moving is one type of mechanical energy. So this person is burning up 200 joules of energy every second. In 1 kilocalorie, there is 4,186 joules. So I think that's a conversion factor. If the person were to go twice as fast, so if we had them going twice as fast, let's just see how that would change. So if they went 3 meters per second instead, then this would become a 3. And when you square 3, you get 9. And when you take 9 times 100, you get 900. And you take half of that, you get 450. So, yeah. So this would become 450. So just if you increase, look, we only increased the speed a little bit, but we ended up more than doubling the amount of energy involved with it. So that's how to just use this new thing called kinetic energy. But let me erase this and then show you how to derive the work-kinetic energy principle. Okay, so the way this one starts is I take one of the formulas for the 4 formulas of constant acceleration, and the formula I want to work with looked like this. V final squared equals V initial squared plus 2a delta x. And remember, each one of those things was basically a vector. And I want to solve this thing for a, so if I solve it for a, I'll say a equals V final squared minus V initial squared over 2 delta x. Okay. And for a moment, I'd just like to change this delta x into d. So if I may do that, just change the delta x here into d. Okay, for distance. Okay. Now, on the previous video, I was showing you how to get the work, and so the work net is defined as the force net times a distance times the cosine of an angle, and whichever way the net force is pointing, the net work will be going in the exact same direction. Okay? So when we're talking about, whenever we know which way the net force is pointing, the object moves in the direction of the net force. So if we have the object moving in the exact same direction as the net force is pointing, whenever they're working with the word net, then the angle is always going to be 0. And the cosine of 0 comes out to be 1, so we don't even have to write it. Let me just keep going. So the work net equals, well, another way to write force in chapter 4 was m times a times the distance. And now I want to make a substitution. So I want to say, instead of calling A this way, I want to call A this stuff. So I could say the work net equals M times V final, which is squared, minus V initial, which is squared, over 2 times the distance, and we multiply by the distance again. And as you can see here, hopefully, the distance value cancels out. So we have a d in the numerator and a d in the denominator, so that distance will cancel out. And if we just take this and make it into, multiply, use the distributive property and multiply the m in, and then separate it to 2 different fractions, what you'll see is the work net equals 1/2 mv final squared minus 1/2 mv initial squared. And what you're looking at here, it's called the Work-Energy Principle. It really deals with the net work and the kinetic energy. And we're talking about the change in the kinetic energy. So whenever you have net work being done, well, if there's net work, that must mean there was a net force. A net force must mean that something was accelerating. Accelerating means the velocities change. So we will definitely have a change in the velocity beginning and the velocity final. So work net would equal, anytime we talk about something, the final something minus the initial something, it's always delta. I've run out of room down here, so if I may, I'm just going to go back up and rewrite that line. So I've rewritten this line up here. So we have the work net equals 1/2 mv final squared minus 1/2 mv initial squared, and this is called the kinetic energy final, and minus, this is called the kinetic energy initial, and this equals work net. So the final step would be work net equals the change in the kinetic energy. So from all that, we come up with something like this, where we have the net work is equal to the change in the kinetic energy. I have this problem here behind me where it says we have a 50 kilogram box and it's being pulled vertically upward by a rope with a tension of 550 newtons. So tension is a force inside of a rope. If the box moves upward 20 meters, find the net work. We should specify, but find the net work done on the box. So I recommend that you draw a free body diagram for all of these problems. And for the free body diagram, you basically would draw a box. It's being lifted vertically, so I'll put a rope on it and say that this is going upward. And the tension in that rope equals 550 newtons. And they told us right here that the mass of the box is 50 kilograms. So I will point out before I move on that many students make a mistake because they don't draw every single force involved. So many students would look at this and quickly say there's only one force on it, and that's the force of tension, so that must be my net force, and I must be moving up 20 meters, so they'd say 550 times 20, and they think they've got it. But the problem is they're not thinking about all the forces that can act on objects. So anything that has mass has weight. So this thing also has some weight. And the weight points down. And the weight is mass times gravity. So if you plug this in, the weight is 490. Okay? So we've got work being done by a few different things here. We've got work being done by the tension in the rope. We've got work being done by the weight of the object. And that's it. These two things together will give us a net force, and we've got the work being done by the net force. So if I wanted to simplify the net force, I would redraw the box of 50 kilograms, and I would say I'm going to add up these two vectors. So if I wanted to do the net force, I would say the sum of all those forces, it would be a positive 550 newtons plus, because the other one is pointing downward, I'll say plus a negative 490 newtons. And when I do that, it comes out to be a positive 60 newtons. So my net force is a positive 60 newtons. It's moving upward. So I'll do like this. So my net force is a positive 60 newtons. Okay. Well, what's the formula for? The formula for work would be work equals a force times a distance times the cosine of an angle. So in this particular case, we want the net work. So the net work would be the work net equals the force net, which we just saw was 60 newtons. We multiply it by the distance it's going to move through. The original question said it moved through 75 meters. No. The question said it moved through 20 meters. The cosine, whenever we talk about net forces, the net force and the direction of motion will always be the same. So this particular thing, the net force and this would be in the same direction. And this is going to come out to be 1,200 Newton meters. Or I could say that this is 1,200 joules. It's the same thing, either way. So now I figured out the net work. Okay. They could have asked what is the total work being done by the tension in the wire, and then they could have said what is the total work being done by the weight. So if we did that, we would have also come up with, if we tried to add them, we would have come up with this. So for instance, the work being done by the tension, it would equal the force of the tension, which is 550. The distance is 20 meters. And we'll multiply that by an angle, and we'll say the cosine of 0 degrees in this case, because the box is moving upward and the tension is pulling upward, so the angle between an upward arrow and a second upward arrow is 0. So if we did that on your calculator, you would get this, positive 11,000 joules. So that's how much work the tension is doing on this box. So you see, usually if something is being lifted up, something has to be pulling on that rope. It could be in the olden days when someone had a bucket of water in the well and they were lifting up the bucket. Nowadays it could be an engine, a motor, and it's spinning something, and there's some wire being wrapped around the spindle and the cylinder, and the thing is pulling up. So something is doing this work. Okay, but that's how much work the tension force is doing. How much work is being done by the weight of that object? So the work being done by the weight would equal the weight. It's 490 newtons. The distance it's moving is 20 meters. And there's an angle associated with this. In this case, the box is moving up, but the force is pointing down. So that would be an angle of 180 degrees. So if I plugged in here the cosine of 180 degrees, so if you plug these numbers in, you would get 9800 joules, and it's a negative. Okay. So sometimes when we have work, some of the work puts energy into the system, sometimes the work takes energy out of the system. In this particular case, we have 490 newtons times 20, we have a negative 9,800 joules of energy is being removed out of the system because we're doing work against gravity. If I let anything go, here's my calculator. If I let my calculator go, it's just going to want to fall straight down, because that's what this force of weight does. It tries to pull things down. So if anything is lifting up, we're doing work against gravity. So the cable, the engine, whatever it is putting in 11,000 joules of energy into the system, but this thing called weight is taking out 9,800 joules out of the system. If you add those up to get the total, when you take 11,000 on your calculator and you add a negative 9,800, what you'll get is a positive 1,200, which is called the net work. So in a roundabout way, I've just shown you how to go about getting the net work right here. This next section is talking about potential energy. And potential energy is stored up energy. So if we store up something, that means we're hoping to be able to use it later. So the two types of stored up energy this chapter talks about would be, say if I picked up something and I lifted it up high. By lifting it up high, I just did work on it. I basically was pushing this thing through a certain distance. So I did work, and by doing work on this thing, I just gave this some stored up energy, because it's not moving, so it has no kinetic energy, but it's now higher up than it was a moment ago. So it's got this stored up, and we call it gravitational potential energy. If I were to let it go, then the gravitational potential energy, which is stored gravitational energy, then what would happen is, if I let it go, it's able to fall down, and it would fall down. So out of nowhere, with nobody touching it anymore, with nobody pushing, I just let it go, and this thing would start to fall. And it would fall, and as it's falling, it would be gaining a certain type of energy called kinetic energy, and it would be gaining the kinetic energy because it would be losing potential energy, height energy. So if anything is lifted above where it started, it has this new type of energy called gravitational potential energy, which is stored up energy, and I call it energy of height. So if you were to go skiing, basically you sit in a chairlift, and the chairlift will be pulling you up a mountain. So you've got this cable that's pulling you up a hill. So the cable is doing work on you, and it's doing work on you, and you're getting this stored up gravitational potential energy. Well, later, you're at the top of the hill, and you just lean forward, and technically, you will start to move. You will start to slide. You'll go faster and faster as you're going down the hill, because your height energy will be going down, and your speed energy will start to go up. So if you gain kinetic energy from something, you have to be losing another type of energy. Okay? In the last few sections, I was talking about me pushing on a box and doing work. If I push on the box and do work, I am getting tired. I am losing some of my own energy. It's leaving me. I'm feeling weak. I'm feeling fatigued. I'm feeling like I have no more energy because I've given my energy to a box. So if I push it across the floor, the box may have been motionless. Next thing we know, I'm pushing it and it's moving. So it's gaining potential energy. It's gaining kinetic energy by me because I'm doing work on it. But in this case, if I lift up something and keep it here, it has stored up energy in it. And when I let it go and it falls down, it will become kinetic energy as it's falling. And it has to get that energy from someplace. So we would get it by the loss of gravitational potential energy would be equal to the gain in kinetic energy. There's different types of stored up energy, and we focus on the main one here, which is called gravitational. So what I've written here is gravitational potential energy, and remember, potential energy means stored up energy. It's the energy of height. Anytime something is changing its relative height, it's changing its gravitational potential energy. So we write it this way: P for potential, E for energy, and we have a subscript here, G, for gravitational. It equals M, which is the mass, in kilograms, G, which is gravity, which is in meters per second squared, and Y is for the height, in meters. Many books will use the letter H here for height. So many books you'll see M times G times H. Lots of books also use this letter Y, because in chapter 2, when we talked about the Cartesian coordinates, we said if you move in the vertical direction, up or down, we're going along the Y axis. So that's the only reason why they're using the letter Y here. Okay? So it's another energy. So the units of this is going to be, again, joules. Okay. So every type of energy has the same units, which are called joules. Here I have a problem, and it's a problem with gravitational potential energy. So it's a sample problem. So in words, let's say I have a 65 kilogram person standing on the platform on the pool level. So they're standing basically at ground level, and they're about to climb up a ladder. And when they climb up this ladder, when they get to the top, they're going to be up 20 meters higher than they were at the beginning. So one question could be is find their potential energy at the beginning, find their potential energy at the end, and find the change in their potential energy. So you see, if I find the potential energy at the beginning, so they're going to start here. So I might say the potential energy gravitational at the beginning is equal to mass times gravity times the height initially. So I plug that in. 65 kilograms times 9.8 times 0 meters. Well, this one's easy to calculate. Anything times 0 is 0. So they have 0 joules of energy. If I figure out what's their potential energy at the end, I would say mass times gravity times the final. So I want to figure out the potential energy at the end, I would take mass times gravity times the final displacement on vertical, and it would be 65 kilograms times 9.8 times 20 meters. Well, that one's not so simple. You just have to plug that in to a calculator. And this number comes out to be 12,740 joules. Okay. So a question could be, what's the change in the potential energy? Gravitational. Anytime you see the delta, it's for the change of. So we would talk about the potential energy final minus the potential energy initial. And in this particular case, it would come out to be a positive 12,740 joules. Because we took this number, the final potential energy gravitational, and we subtracted away the initial, and we came up with this value. Okay. So the person basically gets up to the top. Okay. So if the person is at the top, how did they get? The question might be, how did they get this much gravitational potential energy? Well, they physically pulled themselves up the ladder. So they grabbed hold of the ladder in each rung and they pulled themselves up. And then when they did that, they basically did work on their own body. So when they were pulling themselves up, they had to apply a force that was equal and opposite to their weight. So the work that this person did, work by the person, was equal to the force equal to their weight. So the weight was trying to pull them down, but they had to have an equal force going up. So they did, what's your weight? Your weight is your mass times gravity. And then what else did they do? Well, they moved through a vertical distance. So they went through a certain distance. And in this particular case, can you see how the formula is exactly the same? The work they did, M is here, G is here, and the distance that they moved through the vertical displacement, it's going to be the same. So your potential energy is equal to the work you would do if you climbed up that ladder or if you ran up some stairs. Okay. So that's how that happens. And what if the person got to the end of this ramp? So if the person was at the end of this ramp and was just standing there and was ready to dive off, so what would happen is, if they step off, then what starts happening is they fall down, and they fall down, 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 and they go faster, faster, faster as they start to lose their potential energy. Because when your height is going down, that means your potential energy is decreasing. So if your potential energy decreases, something else has to change. You can't just have energy disappearing. So if my potential energy is going away, then there has to be some other energy involved that's going to increase. And the thing that would happen, as you all know, if you step off a diving board, you will start to go faster, 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 faster. So when this person steps off that board, we're going to find out that they're going to have 12,740 joules of kinetic energy. They're going to hit the water with a speed. They're going to be moving, and the energy of motion is called kinetic. They'll have that much kinetic energy. There are many different types of potential energy, and in this chapter we deal with two of them. So one of them is called the potential energy gravitational, which is the energy of height, and this one is a different one. This one's called the elastic potential energy, which is the potential energy stored up in a spring or an elastic or a bungee cord or something to that effect. So we just use the word here spring basically, but any type of a thing that has a material that's like an elastic, then it has stored up energy. So what do I mean by stored up energy? Well, if you've been to the circus performance and you see a person being shot out of a cannon, well, they're not actually shot out of a cannon. Inside of a cannon there is a spring and there's a platform, and somebody compresses the spring down. A person climbs in there, stands on the platform, and when now there's a lot of stored up energy in that spring, and when somebody lets it go, the spring is going to lose all of the stored up energy as the spring goes back to its equilibrium position, and all of that stored up energy is going to be transferred to kinetic energy. So when the person is coming out of the cannon, they have kinetic energy equal to what the stored up energy in the spring was. If you play pinball, in pinball at the end there of the table, you have a little handheld plunger almost. You grab hold of this little thing and you pull back. When you pull back, you're compressing the spring. You've done work on it because you've pushed through a distance. So you've done your work, and the amount of work that you did pulling that plunger back, well, then there's going to be a ball dropped on it inside the machine. When you let it go, all of the stored up potential energy in the spring is going to be transformed to the ball. So when the spring goes back to its equilibrium position, then that means that the ball now has a lot of kinetic energy that it got from the spring. They have these kid Nerf type of guns or something like that, so they have this spongy material, and you would take it, and the way they used to make them anyways, they would have like a little Nerf dart, and you would take the dart and you would push it into the gun. So when you're pushing it in, you're doing work. You're pushing through a distance. While you're doing that, you're compressing the spring. So if the spring gets compressed, there's stored up potential energy in the spring. And later when a kid goes and triggers the gun, then a little dart will shoot a little bit across the room, and maybe if it has a suction cup on it or something like that, they could try to hit it and have it stick to a wall. So the dart will gain its kinetic energy because there will be stored up and potential energy in the spring. And for a spring, we call it this: potential energy. There's the P and here's the E, and they say elastic. In this book they use EL. Some books will use spring. Some books will write out the whole word elastic. So we have potential energy elastic. It equals to 1/2 times small letter k. Small letter k is called the spring stiffness constant. So every spring has a certain stiffness to it. So if it's a very, very hard to move type of a spring, if you grab the two ends of the coil and try to stretch the spring apart, if it doesn't move apart easily, it's got a huge number for the spring stiffness constant. Okay, the springs that hold up your car could be 10,000 Newton per meters. Okay, if you took apart a pen and you had that little tiny spring there, and if you played with it, it's easy to push it in. It might be easy if you grab the ends of it. It might be easy to pull it apart. If it's easy to compress or stretch the spring, then the spring stiffness constant will be a very small number. And you know, one of those pens had the spring in it. Maybe that's some number like 10 newtons per meter. So K is how stiff the spring is. And the X in this formula here, when we did chapter 2, X meant the displacement. Well, it's the same thing almost, but it's not just any displacement. It's the displacement from equilibrium. So if we every spring wants to go back to equilibrium no matter where it is. So when you take a little spring out of a pen and you squish it together, you've squished it, you've moved the end of it away from equilibrium. So when you let it go, it wants to spring back and eventually stop at equilibrium. So when we say X here, it's not just the distance something moves, but it's the displacement on the end of the spring from equilibrium. Okay. So there is a formula that relates a force and things like that, and the formula would be a version of Hooke's law. And the version of Hooke's law would be this: if you look at the force external, meaning if I took a weight and hung a weight from a spring, then it would equal to K, the spring stiffness constant, times X, the distance that it's being stretched away from equilibrium. So you see, if I put any mass on a spring whatsoever, it would end up pulling the spring and stretching the spring away from the equilibrium position. So what I have here is I have a spring, and I've just attached it to a little hook I have near the ceiling here. So this spring, it's springy. It can pull down as much as I want, and the further I pull it down, I feel more and more force. So as I'm pulling it down, I'm feeling greater and greater force. So when I move it like, okay, I don't know. So that's where it is in equilibrium. If I move it down this far, that's like 2 inches, I feel a little force. If I move it down 4 inches, I'm feeling much more force. If I move it down 10 inches, I'm feeling greater force. In fact, if I let it go at each of those places, if I let it go right here, you would see it snap up, and you would notice that it snaps up more violently than if I just pulled it down an inch. So it's saying that the force I'm feeling, the external force, is equal to the spring stiffness constant times how much it's been displaced. So if I took my meter stick here and I went to the pole, and I just measured it really roughly. I'm looking at the end of this spring, and it's approximately at 35 centimeters. So I'm not doing anything really exact here. It's approximately at 35. So when that spring, let me just erase some of this back here. So what I'm drawing here is the ceiling, and I have a little spring, and I'm just saying that it's approximately 35 centimeters. Okay. Of course, I just wrote right where you can't read. So it's approximately 35 centimeters. Okay. And if I take a mass, now this is a mass, and this mass says 200 grams. If I put the 200 grams on this carefully, you see it just stretched the spring out a certain distance. So if I go and I check this, I'm looking at the exact same spot on the spring, and it looks like it's around 55 centimeters. Again, I'm doing it roughly. So when I put that mass on it, the spring has stretched, and I have this little weight on it, this little mass. This mass is 200 grams. And now the bottom of the spring is at a height of 55 centimeters. So with that information there, I can tell you how stiff this particular spring is, because this formula will tell me what's happened. So with no weight on it, you can see it's bouncing a tiny bit. With no weight on this thing, it would, I mean, if I left the room and came back in 15 minutes, this thing would be stationary basically. So that's its equilibrium position. And whenever I move it away from its equilibrium position, it wants to come back to it. So if I put the weight on it, okay, and then I would just to let it go right away, take it off, you would see a sudden, well, that didn't work at all, but you would see it snap back. So I'll put it back on. So you see this amount of weight and this amount of mass, and mass is not just mass, that's a weight. When we have mass exposed to a gravitational field, we have something called a weight. So here we have this distance it's stretched. So what is the difference between 35 centimeters and 55 centimeters? Well, that thing just stretched 20 centimeters. So here I would say that it equals K, and it would be 20 centimeters. We have to convert it to standard units, meters. So this would be 0.2 meters. And what is the external force? Well, the external force of this thing is called the weight. So the weight of this thing would be mass times gravity. So since this mass is 200 grams, I could say the weight pulling it down is equal to mass times gravity. So it would be 0.2 kilograms times 9.8, and that equals to 1.96 newtons. So this is the external force, 1.96 newtons. 0.2. And if I took my calculator, 1.96 divided by 0.2 comes out to be the number 9.8, which that's a coincidence. It has nothing really to do with gravity. That's just the numbers, the way these numbers have come out. So this K is coming out to be 9.8, and it's newtons per meter. Okay. It's not a very stiff spring. You can see it. It's easy to stretch. If I let it go, it'll bounce up and down, and that's not the topic for today of this thing oscillating up and down. But the number here, 9.8 newtons per meter, is telling us how stiff that spring would be. So if I go back to the previous formula that I had, let me erase a little of this. So if I go back to the previous formula, it said the potential energy elastic equals 1/2 K times x squared. So if I plug that in, I would say 1/2 K, stop this bouncing. Okay, so 1/2 K we just said was 9.8 newtons per meter, and x, we measured it as 0.2 meters, and we have to square that. So if I square that thing, 9.8 times 0.5 times 0.2 squared, it comes out to be 0.196. and that's the potential energy elastic. Which means there's stored up potential energy in this particular spring right now. So if I pull it down, so I could even take the weight away. So it's approximately right here. So if I try to hold on to this and take this away, let's see. Okay. So right now this spring is at about the same place, and I have that much elastic potential energy. What does that mean? It means when I let it go, it will spring back in such a way that the elastic energy will turn into kinetic energy. So the end of this spring will be moving with such a speed that we'll have a certain amount of kinetic energy there. And as I let it go, you see, it just kind of flung up somewhat violently. It wasn't that violent. If you wanted to see, I mean, it would be less. You could see all these different things. If I pull it down barely an inch and let it go, so if I pull it down about an inch and let it go, it just does something like that. If I pull it down, you know, much more, if I go and I pull this thing down much more and let it go, then it'll just be more violent. That was pretty cool. Okay, so that's how to use the formulas of potential energy elastic.